Well, I don't really want to go into the details of how to do that because this is sort of the technical stuff. You can look it up. It's a method here that I use, or that many others also use, is called successive over-relaxation, SOR. Okay, and it's used to solve an equation where you have more than one unknown, 5 unknowns. And the form of this iteration, so what it is an iteration, so you repeat a calculation many, many times until you meet a certain condition, and this is the shape of the form of this iteration. Okay? And it has a parameter in it called omega. It's this omega here, and actually implies if you use a value larger than 1, it means over-relaxation. We overestimate a certain component. That's why it's called. Anyway, we're not going into the details that much. You can work that out. And essentially gives you a little bit. You can look through the text of how you do it. But essentially, during each time step of the routine, go through a separate iteration loop that updates. Okay? What's also in there, and this is the only reminder here for me, is every time step you also have to do, or during each part of the iteration, you also have to do a correction pressure near the surface. Okay, you need to do a vertical integral, and so it turns out to be anyway. So if you had to do it, you would see what I'm. You also have to implement boundary conditions that SOR iteration. So that's how the structure looks like. So you have your time iteration. You have your values for UW and Q. You calculate the first guesses. Okay? This is the first guess value. Then you set the initial conditions for the SOR iteration. And then you start your SOR iteration. You repeat, and you stop this iteration. Just to be precise, you stop it if the error that you make in terms of the volume conservation is very, very small. And that you might actually repeat it within a time step, maybe 100 times. Okay, this is what we call SOR. Now we can test it. After all this, there's no way around it. Okay, so because pressure is on the right-hand side of these equations, you have to use a method like this. There are other methods, but it turns out to be very, very complex to actually derive a good numerical model for these. But we can test it now. Okay, let's test it.